Okay, so now we're at step 2. Connor, tell me what step 2 is. What time region?
T is greater than or equal to 0.
Yeah, and why? What are we trying to find?
We're trying to find the
Tau.
Tau, that's it. We want to find tau. So now,
time constant, basically.
yeah, so we're going to draw it for time greater than 0. Our capacitors stay capacitors because we're not in DC steady state. Stuff is changing. Our, what's our switch position? Who are we left with here? Pavel, what's our switch position? Up or down? And Bobby, you're going to be on deck for the next one.
It is down.
It is definitely down. And so that just looks like this. Now we've got our 9 amp source. It's just running around here.
Shouldn't the source be a short? I mean, open? For it.
Shouldn't the sort, so it's down. And so now that it's down, that switch is connected to make this a short. So we got that short. And it's not connected, so this is an open. Does that make sense?
No, I mean, when you're finding tau, shouldn't your sources be either shorted or opens?
When you're finding REQ, they should be, and that's a subset of finding tau. So our first step is to draw it for time less than 0. This is what it is for time less than 0. And now we're going to take all of our independent sources and either short them or open them to find tau. Yeah, that's right. So now we'll open this up, and if it's a voltage source, we'd close it off. And we'll ask, how much resistance does this capacitor see? We don't even really need to do that though here because this isn't part of our circuit. But Pavel, you're right. In general, we would zero this guy out. And so our next step would be to ask, what kind of resistance does this capacitor see from its perspective as we zero everything else out?
I thought the switch was supposed to close when time equals 0, when time was greater than 0.
So what this arrow says is that when time equals 0, it's going to move in the direction of the arrow. So if it's moving in the direction of the arrow at time equals 0, for time greater than 0, will it be up or will it be in the direction of the arrow?
I figured it'd be in the direction of the arrow.
That's right. And so I'll redraw this in a moment, but if it was in the direction of the arrow, it would be now down.
Oh, okay, no, I see now. That makes more sense. I see.
Yeah, let's go back.
I just read you the circuit in a different way, but it's the same thing.
Yeah, same thing. Okay, so now let's get back to this guy. How much this would be 0, so that would be an open. Hey, we really don't need to worry about it since we're concerned about this impedance on the left, and we know no current can go through this one wire because we could just draw a circle around it like this. Total sum of currents coming out has to be 0. There's only one wire, so therefore the current coming out of here has to be 0. If there's no current going in or out of this thing, then if we only care about the stuff on the left, we can ignore it. That's the rule for ignoring it. So we're left with this. What is that REQ?
Isn't it just 6? Or it's 6 in parallel to 12?
Yeah, that's it. It's equal to 6 in parallel with that 4 plus 8. Because these guys are in series, and then these two are in parallel. So now we can say 6 in parallel with 12. Now, when you see something like this, there's three ways to solve it. The way I definitely do not want you to do, even though it's correct, is to say it's equal to this. Because you need to pull out your calculators for that. So although correct, don't do that. A better way to do it is to say product over sums. That is better. Problem is that off the top of my head, I'm not good about dividing things by 24.
Plus 12, sir, not 18.
Is it 18? Oh yeah, thanks. You already made a mistake. But instead, so this works, but it's not ideal. Instead, what I want you to see is that if you've got 6 in parallel with 12, whenever you see things that are multiples, do you realize that you could make that 6 by 2 12s in parallel? Is that just obvious to everybody that that's your 6? And then you've got an additional 12. Now you've got 3 12s, 3 identical resistors, all in parallel. what does that resistance have to be by inspection?
4.
4. And if you don't get that, and if you like the product over sums, that's fine. I'm just telling you a even faster way to make more complicated things just fall out. Like for instance, if you had a 12 in parallel with a 24, I mean, that would be hard in your head to figure out what's 12 times 24 over 12 plus 24. But if you see that 12 as just being a 24 in parallel with a 24, and then you've got an additional 24, you can just say in your head, hey, that's just going to be what? What's 3 24s in parallel?
8.
8, yeah, without pulling your calculator out. Okay, so that's your REQ. And now you can find the goal, which is to find tau, which is equal to REQ times C. So that would be 4 times 1/16. And so that would be 1/4 second. And that is your goal for step 2. The big deal with step 2 is finding that Thevenin equivalent.